311, hyperbolics. Let's get after it. I would go through and start to tell you what hyperbolics are all about, but I think you have a little bit of an exploration in this later. I'll tell you about it, I don't know, maybe in a few minutes. Let's get into this though. We have a definition of this thing called a hyperbolic function. Okay, we're not sure what it is yet, but what we can see is it kind of looks like trig. You see the sine, the cosine, the tangent, the cosecant, the secant, the cotangent. But now there's this little h. And that's signifying that we're dealing with a hyperbolic function. So we're not dealing with triangles here. This is not trigonometry, but some of the rules still do apply. Before we get into what sine hyperbolic and cosine hyperbolic are equal to, let's just take a look at some of the identities so we can get familiar with it and recognize we already know a little bit about this. Well, just like in trigonometry, where cosecant is equal to 1 over sine, hyperbolic cosecant is equal to 1 over hyperbolic sine. So those rules still hold. Secant hyperbolic, well, that's just the same thing as 1 over cosine hyperbolic, and we would hope that would be the case. Cotangent hyperbolic is equal to 1 over tangent hyperbolic, and as we can see, tangent hyperbolic is equal to sine hyperbolic divided by cosine hyperbolic. Well, now let's get into what is this? This is some sort of definition. Where it's because somebody said so. Sine hyperbolic is equal to e to the x minus e to the negative x divided by 2. And cosine hyperbolic of x is equal to e to the x plus e to the negative x divided by 2. The only difference is the sign in between. So let's go explore with that before we get into anything else. And I think maybe we can go through and graph. So let's take a look at sine hyperbolic and cosine hyperbolic. And before we do, let's just look at sine hyperbolic. I've written it out and then broke it up into a couple pieces. This denominator trick I've been trying to get through with y'all, where if we can always break up the numerator, so now we have 1/2 e to the x plus negative 1/2 e to the negative x. And we're going to do something called graphical addition. Just a way where we can put these two things together and we can see it. This might be the first time you ever get to see this. So what we're going to do is we're going to graph what's in blue, just by breaking this up right here in blue, and we're going to graph what's here in purple. Well, we can graph e to the x. This isn't all that bad. E to the x, let's zoom down a little bit, and e to the x looks a little something like that and takes off. The only thing is we just need to know that y-intercept. We're just going with basic shapes here. Well, e to the 0th power would equal to 1, and then 1 times 1/2, that would just be equal to 1/2. Okay, cool. Well, let's go graph our other function. So this is going to have the same shape, but the changes that we have here is we have a negative inside that exponent, and we have a negative out front. So the negative on the exponent is actually going to take our graph, and it's going to flip it about the y-axis. And then the negative that's hanging out down there, or right in front of the 1/2, that's going to flip this about the x-axis. So we just have to mirror this. Imagine you're folding a note to somebody. Fold it over and then over again. How would it end up looking? Well, we'd have the same horizontal asymptote just going in 2 different directions, but it would have the same basic shape, except now our y-intercept would be negative 1/2. So there they are. We've graphed the two things. And what graphical addition tells us is we're going to be trapped between the two things. If we look off to the far left, if we were to add these two things together, the limit is x tends to negative infinity. Over in this direction, the negative infinity direction, well, the top part doesn't seem to do anything, does it? It's absolutely nothing. It's going down to that. So I think that what our graph is going to end up being is coming up like this. And as we get closer and closer, what's 1/2 plus negative 1/2? That's 0. And then as it goes through its asymptotes, it just takes off and it's going to follow this through. Now let's just jump over and we'll graph that a little nicer in a second. Maybe if you didn't catch it the first time, maybe you'll catch it this time. With cosine hyperbolic, well, we have the same two things. The only difference is our second function, or the second piece on the right, doesn't have a negative. So we're going to go through and try and graph this again. Our 1/2 e to the x, we got that one from the first. 1/2 e to the x from the first one. Takes off, and there's our exponential graph going right through 1/2. Now we're going to have that 1/2 e to the negative x, but now it's only negative on the exponent, which means we're going to revolve about just the y-axis. So we just have a bit of symmetry here. So we'll come back and go right through there. All right. Now we're going to play that same game as to how we graph. Well, it looks like on the outsides, we're going to, since what's in blue on the left, what's in blue going towards the asymptote, that's going towards 0. That's not going to add anything to this. So the graph's going to just go and follow this little parabolic shape, not a parabola. And then 1/2 plus 1/2 is 1. So we'll go through there and it takes off. And boom, and it looks like a parabola, not a parabola. So let's clean it up and get a little bit better of a look at this. And we'll see our graphs. So for sine hyperbolic of x, our graph will look a little something like this. For our y is equal to cosine hyperbolic of x, our graph is going to look a little something like this. With an asymptote, or at our y-intercept of 1, and our sine hyperbolic with an intercept of 0. But why we want to look at this is actually because of the domain. And that's really just so we can talk about this. The domain is our x values. And it looks like our x values can really be anything we would like. For both, right? Our domain, any real number is going to work. We are chill with that. We can plug whatever we want in. And now when we look at the range of sine hyperbolic, well, we see that our y value, sine hyperbolic, that could be anything as well. So our y values can also be all real numbers. However, when we go to look at the range, well, it looks like our y values will need to be greater than or equal to 1. Cosine hyperbolic is never less than 1. Now we also have one for tangent hyperbolic, and I'm not going to go through the whole rigmarole to show you how that one worked out. But this one is just going to look very similar. So tangent hyperbolic, it looks very similar to inverse tangent, except it has horizontal asymptotes at -1 and 1. So what this tells us is that we have a domain. Oops. Let's write domain first. We have a domain which we can plug anything we want to into our function. Yet our range, well, all of our values are going to be trapped between -1. Oh, did I put that in there? Trapped between, that's a horizontal asymptote. It'll never achieve that. And 1. So our heights, it's just smashed in between it. So there's the beginning of sine hyperbolic, cosine hyperbolic, and tangent hyperbolic.